And I would like us to continue with projectile, black hole fracture, and several other topics. But maybe before we do that, maybe let's try to do the previous thing and see if this classical mechanics thing is clear enough for you. So do you have any questions about last week's presentation? Hello?
No, sir.
Do you have any questions about last week's presentation so that I can answer them maybe before we start today's topic? So I'm going through the last week's presentation, and maybe if you think that you need to ask something, please ask. So basically we have done projectile rotation, and then of course escape velocity and orbital velocity, law of gravity of Newton, solid mechanics, free body diagram, inclined plane, without friction, with friction, okay, block stacking problem, okay, spring, pendulum, that's pendulum, this is spring, oscillation, waves, interference of waves. Do you have any questions about the last week's presentation? Any questions? Or maybe about this week's presentation? Any questions? So that was last week, and this is this week. Okay, if there are no questions, maybe we can start. Let me see if my charger works. Okay, it works. Okay, so we continue with collisions a little bit, but in a bit different way. I would like to discuss with you a question. Do you think Messi or Ronaldo will be better at kicking the soccer ball accurately and precisely? Messi is small and Ronaldo is big. Messi is small and Ronaldo is big. Messi has small foot, Ronaldo has big foot. So who do you think can kick the ball more accurately and more precisely? What do you think?
Messi, sir.
Can you see this slide number 3?
Yes, I see.
It says that small foot is more likely to be more accurate and more precise because it gives less random error and less systematic error. And the small foot can kick more accurately and precisely because it can kick closer with respect to the center of mass of the ball. So for that reason, usually small soccer players are more successful than big soccer players. For example, Maradona, Messi, Modric, Arshavin, the small people, they're usually better at kicking the ball more accurately and precisely. Yeah, and the opposite examples can be Ronaldo and maybe another guy, I forgot his name, the tall guy, I think Norwegian guy, but it's less likely to happen. So if you play soccer, if you like soccer, maybe you can think about that and relate this to physics. What do you think? Yeah, I'm asking you this question. Maybe you can answer it and also explain why. Yeah. Any questions about this kind of sort of collision between the soccer ball and human foot? Okay. Okay. So then maybe we can move back to projectile. And I would like us to find the minimum velocity and corresponding angle of release. So if you remember the projectile, the parabolic type of motion requires the initial velocity. And if you want to hit a point somewhere, you must make sure that your initial velocity is big enough, right? And then if it is big enough, then you can hit the point, finding the angle of release, yeah? But if your initial velocity is not big enough, you just cannot hit the point. So let's look at how we find the minimum velocity. So as you can see, maybe I can correct as I speak. Oh, I'm sorry. Basically, we write the equations of projectile, slide 6. We express velocity. V in this case is initial velocity, V naught. So I just make it simple, V. And then you take the derivative from V and you equate it to 0. Okay, derivative with respect to tangent of the angle with respect to t. And from here, you can find the angle t, and basically you can find, what those angles are that allow you to hit the target, T1 and T2. Can you see? X and Y are the coordinates of the point. It can be any point on the plane. Okay, so by doing this, you basically find the angle of release, which allows you to hit the given point X and Y. Okay, so let's move to the next slide, and this is basically the code. It gives you two angles of release, and then it calculates them in degrees. So we choose the first tangent, the first angle of release, because it gives us smaller time. If you want to hit your target, it's better to choose smaller angle of release than bigger angle of release, so that your projectile will hit the target earlier. Any questions? Any questions about projectile? As you can see from slide 6, your x is given at any time t, and your y is given at any time t. You can express y through x, this equation, and from here you can find v squared, yeah, from this equation of y and x and tangent a, yeah. You find v squared through tangent and x and y, okay. Then you find the smallest possible velocity by taking the derivative from this equation, v squared, and equating it to 0. Okay. From here, you will get the corresponding angle t, yeah? And when you calculate angle t, you plug this angle into this equation for v squared, and you get the minimum velocity, yeah? So you get the minimum velocity, and then you know whether you can hit this target x and y, or you cannot, yeah? So basically, we know everything about projectile. Projectile is solved completely. This x and this y solves projectile completely. Okay. Now we can find minimum velocity of the projectile. Yeah. So for any point you want to hit, you can always find minimum velocity. Okay. Is that clear? Please do ask questions. I'm still thinking about your previous questions regarding how mechanics is used in information technology and that sort of stuff. I think I know the answer to this question. Maybe I can tell you a little bit later when we finish this lecture, okay? Anyway, for any point in two-dimensional space x and y, you can find minimum velocity v, minimum initial velocity v, sometimes we call it v naught, to hit this point, any point, okay? And you can find the corresponding angles of release. T1 and T2, those are tangents of the angles, yeah? And if you want to hit your target as quickly as possible, you choose the smaller tangent, so the one with minus, because the one with plus will be bigger angle and slower projectile. It will take more time to hit the target, okay? So let's look at slide 7. This is the code to find the velocity and the angles of release. Yeah. Minimum velocity of projectile. Yeah. When you find your angle of release, T1, for example, then you can find velocity, minimum velocity V1. Okay. So this is the code, and hopefully it will help you. In this case, as you can see, x is 11 meters and y is 2.5 meters. This is to hit the top corner of the soccer goal from the penalty spot. Yeah, so if you want to hit the top corner of the soccer goal from the penalty spot, that's the minimum velocity, and those are the two angles of release and the minimum velocity you need to hit it. Yeah. But of course, if you want to hit it faster, you can increase your velocity. You can make it as big as possible. You can hit as hard as possible. Yeah. So that your velocity can be much, much bigger than the minimum velocity. You can do that if necessary, if you can. Yeah. So this equation needs to be checked, of course, because it's pretty complex equation. And I was afraid that maybe I have made a mistake. That's why I have created this test number 8. I ask you and I ask myself to check the correctness of minimum velocity calculation. And I ask you to calculate for height y is equal to 20 meters. Yeah. And because it's vertical, x must be 0, but 0 is not allowed because it's discontinuity point of our function. So we take x is very, 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 very small. As you can see, 10 to the power of 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 to the power of minus 9. So 1 nanometer. 1 nanometer. Yeah. And y is 20 meters. So basically we hit the ball, or we shoot straight up. And as you can see from the equation of escape velocity, if you kick your soccer ball up with initial velocity of 20 meters per second, you will actually reach 20 meters. 20 meters. It's easy to see from the equations. If your gravity acceleration is 10 and I give you g10, can you see? So this is the way to test our equations. And if you do that, then you will see that our equations are correct. Let me show you what that is. Yeah. That's another test. Yeah. So this is the test to check correctness of our minimum velocity equation. Yeah. And the next slide, the next test, I would like you to calculate minimum velocity for tangent A being x over y plus 1 over s, which is your student number. S is your student number, which is like 22 million, yeah? 1 divided by 22 million. X is 1 and y is 1. So it's going to be about 45 degrees, yeah? And then you find the velocity for this angle of release. Please ask me questions, because if you are quiet, I don't know if you understand or not. I feel that you don't understand. Can you ask me something, please? Okay, let's see the next slide and maybe it will help. So again, I would like you to find the solution for your minimum velocity plus 1 over t number. In your case, it will be maybe 1 over 20 or 1 over 15 or something like that. Yeah? In other words, your minimum velocity plus something positive. Yeah? So as you can see, you will have your initial velocity greater than minimum velocity. Yeah. So I ask you to do that. And these are the equations of projectile once again. And again, we get quadratic equation for the angle of release. T squared is a tangent. And as you can see, this is tangent 1, T1, and tangent 2. And to make it simple, we just used V instead of V naught, because there are so many V's here. It will be very annoying to write V naught, V naught, V naught everywhere. Anyway, I ask you to calculate the angle of release for this velocity V naught minimum plus 1 over t. Let's say plus 1 over 15 for your student number. And that's what you will get. T1 and T2, these are tangents of angles of release. Okay. And this is the code, yeah? So, yeah. So basically, this is the code for the tangents of angles of release. And you can calculate both of them in degrees. So this is 180 divided by 4 arctangent of 1. It's conversion of your angle from radians to degrees, so that you can see your angles of release in degrees. I hope it's easier for you, and it's also easier for me to see the angles in degrees. If, for example, if you get 1 radian, for some people it's hard to remember that that's about 57 degrees. But if you have, for example, 35 degrees, oh, it's easier for many people. That's why here I convert your angles into degrees, from radians to degrees, okay? So this is the code which solves the problem. So basically, for given velocity, this one, right? V1 is minimum velocity. And then you plus 1 over t. For example, 1 over 15 maybe for your student number. Yeah. And for this velocity, you can find angle of release T1 and angle of release T2. To be more accurate and precise, T1 is the tangent of the first angle of release, and T2 is tangent of the second angle of release. That's why we take arctangents, inverse function, to get the actual angle and then to calculate the angle in degrees. Yeah. Please ask me questions. I think you don't understand. Sorry, someone is trying to open the door. My love, is that you? I'm teaching. Hello?
Hello,
Hello?
sir. Sorry, I'm apologize
Yeah?
that I just joined your class.
Yes.
I want to ask what's the topic of today is, and I see
Yeah.
this title projectile. What is implementation or what?
Yeah. Today we deal with collisions, and we talk about different soccer players, how they can hit the soccer ball in the best way. We
Okay.
started from this, and we have realized that it is more likely for Messi to be more accurate and precise in his kicks, because Messi has smaller foot than, for example, Ronaldo, because Messi is a smaller person. And if you have smaller foot, it's easier to kick closer to the center of mass of the ball so that you can control the ball better. And as we can see, most of the most successful soccer players are usually small people like Messi, Modric,
Oh,
Maradona, Arshavin. So that was the first topic of today, kind of collisions of soccer ball with the human foot and how it works. And then we continued projectile. And projectile is basically a bullet or cannonball, basically. And it's about, hitting the target when you shoot, for example, using some weapons, or if you kick the soccer ball and you want it to hit, for example, the top corner of the soccer goal, for example,
oh,
or you use artillery, for example, if and hit the targets using artillery. And we examine the smallest possible initial velocity. If you want to hit the target on the plane, for example, 1 kilometer away and half kilometer high, for example, right? So X is 1 kilometer and Y is half kilometer, for example, right? Then you can calculate minimum initial velocity necessary for that. And I gave the equations, I proved them, and I checked them using the computer code. I checked that probably these complex calculations are correct, so that if you want to hit the target, you must have minimum initial velocity. For example, if you want to hit your target, your minimum initial velocity must be, for example, 200 meters per second, for example, right? So you cannot have smaller initial velocity than 200 meters per second, because if it is smaller, then there is no way for you to reach your target, okay? And then
okay.
if your velocity is minimum, or if your initial velocity is greater than minimum, then you can find the two angles of release to hit your target. It will be smaller angle and bigger angle. Okay, so you can use smaller angle if there are no obstacles on the way, there are no buildings, there are no hills, so you can hit your target directly and quicker. But if you have obstacles like hills or buildings, then you might need to use the bigger angle of release so that your projectile will fly over the obstacles, such as, for example, hill or buildings. Yeah, is that more clear now?
Yeah, sir. Oh, I see. Uh, is there any implementation of informative techniques?
Yeah, if you want to hit the target, you can calculate minimum velocity, minimum initial velocity. I mean, they do it for weapons, for guns, for artillery, and it's a pretty standard procedure, I would assume. And because there is a lot of military activity these days, maybe it is important for us to to be aware of how the weapons work, sorry, excuse me, and how we can quickly calculate our initial velocity and angle of release. The truth is, though, that this projectile solution is for no air resistance, so it is perfect for like Star Wars, where there is no air, where the projectile can fly without resistance. Yeah, but even for the air resistance, this is pretty good approximation. Maybe if we have time, I will show you far more complex equations for projectile taking into account air resistance. Yeah. For soccer ball, it is significant. But for bullet, for example, it's not very significant. It's not that significant. So for bullet, doesn't really matter whether you have air or you don't have air, maybe only a few percent difference. But for soccer ball, it will be like twice as big without the air compared to the case of the air. So there are obvious limitations to this model of projectile. So your implementation would be, if it is, for example, for soccer ball, if you're a soccer player and you want to calculate how you should kick the ball, then you should probably divide your distance by 2, and your angle of release you must multiply by 2, because the air resistance for soccer ball is significant. But if you shoot a bullet, then you don't really need to change very much. These equations are accurate and precise. Does it help? Hello?
Yes. Yes, sir. Thank you, sir.
I hope it helps a little bit. Okay, so maybe we can continue. Let's look at this statement. I'm explaining here that to hit the target as quickly as possible, we need to calculate minimum velocity, minimum initial velocity. Let me write initial velocity. Minimum initial velocity. Provide maximum initial velocity. So, for example, if you really need to hit the target as quickly as possible, your initial velocity must be as big as possible, and of course bigger than the minimum velocity. Yeah, and then you choose minimum angle of release if you want to hit your target as quickly as possible, because if your projectile flies lower, then it will reach the target quickly. You can calculate the time, and I think we have already calculated the time of projectile's flight, and it shows that the smaller the angle of release, the quicker will your projectile hit the target. So the time of flight will be smaller. Yeah, because you divide by cosine of angle of release. So the smaller the angle, the bigger the cosine. So you divide by bigger number, which means your time of flight will be smaller. Yeah. But just like I said before, if you shoot, let's say, mortar or artillery, and you shoot from behind the hill, for example, or from behind the building, then you may need to choose the bigger angle of release to hit your target. Yeah. The solution gives you 2 angles of release to hit your target. Okay. So you choose whichever is the best for you. If there are no obstacles, you will probably choose the smaller angle of release to hit the target quickly. But if there are obstacles, you may need to choose the bigger angle of release to fly over the obstacles to hit your target. Okay? Is that clear? It's how to hit your target in the best way, provided that you have no obstacles, or in case if you do have obstacles on the way of the projectile, and you want to fly over the obstacles to hit the target. Let's say using mortar or artillery gun. Okay. Okay, so let's look at the next slide. I would like you to prove these equations, remember, for maximum distance and for maximum height, which I gave you, I think, the first meeting, yeah? I didn't prove them, but here at this slide, I proved them, okay? So here is the equation for y velocity. We find the time of the maximum height, okay? And then how do we find the time? We know that the velocity y in the top point, in the highest point, is 0, because at the highest point, the projectile stopped moving up and haven't started moving down. So its vertical velocity is 0. And from here we calculate time h, th, t of maximum height, which is going to be v naught times sine a divided by g. Here v naught is initial velocity, a is angle of release, sine is the known function, and g is the gravity acceleration, which we take as 10 meters per second squared. Okay, and we know that time of the total distance is going to be twice time of the maximum height, because maximum height is in the middle of the trajectory, whereas if you want to know the total time, it will be twice as big, yeah? And then we plug time h into equation for x and time d into equation for y. This equation, where is it? Okay, just a moment. Where is the equation? There we go. We plug x, t for maximum x, td into this equation and th into this equation, and we find that indeed maximum distance and maximum height are calculated using these equations. Okay, maybe you can do that if you want to practice your algebra skills, but maybe you can use my calculations. I hope it helps. So in other words, I just want to make sure that we calculated these maximum distance and maximum height correctly. You know, what if I have made a mistake? No, I haven't made a mistake. It's all correct. Okay. So okay, so I think we are done with projectile for today. Let me check. So these are different topics. Okay. So the projectile can be a bullet, for example, and if you want to hit your target, you use the equations which will tell you how to shoot. If you're a soccer player and if you want to hit the top corner of the soccer goal, once again, the projectile equations will tell you how to kick your soccer ball, with which initial velocity and which angle of release to hit the top corner so that you score with the highest probability, right? If you hit the top corner, usually you score in soccer, yeah? Any questions about projectile and about collisions in soccer? Any questions about anything? Okay. So the next topic that I would like us to discuss, I would like us to calculate angular velocity and linear acceleration. And I ask you to find velocity and acceleration at t degrees latitude, and then we are on Earth, so I give you the radius of Earth, right? We know that angular velocity is basically linear velocity divided by the radius, okay? And basically linear acceleration is going to be a radius of rotation times angular velocity squared. I think we proved it last week. Okay. You know, that's why it's so much easier to write on the whiteboard. Let me try to use the whiteboard. Let me see. Just a second. Whiteboards. No, it says sign in. Whiteboards. Ah, okay. Okay, sorry. I don't know if I can use whiteboard. Let me go back to sharing the screen. Okay. Oh, I see that you sent me a message. Just a moment. Let me check. Okay, just a moment. About small foot versus big foot. Is that the right? Is that right? This also depend on the skill of the players. Yeah, sorry. Of course, it depends on the skills of the soccer player, but we assume that they have the same skills. I'm answering the question that you sent to me through chat, okay? And this one, is this formula also used to estimate when the trains stop? I don't understand this question. Can you explain? Is this formula also used for estimating when the trains stop? What formula? Let me show you. Share the screen. You mean the projectile formula? Hello? Which formula? Okay, maybe we can talk about that later, okay? Anyway, angular velocity and linear acceleration. We need to know that linear velocity is equal to radius times angular velocity, omega, okay? And linear acceleration is equal to radius times angular velocity squared, okay? And because our latitude is t degrees, for example, 15 degrees, then we must multiply our Earth's radius by cosine of this angle of the latitude. So, for example, here in Jakarta, our latitude is, for example, 10 degrees, 10 degrees southern hemisphere, right? So we must plug 10 degrees in our equation, but we must remember that we need to convert degrees into radians, right? And as you can see, we could convert degrees into radians, okay, so that we calculate correctly. And please note that here the acceleration and velocity will be measured in minutes to the power of -1. Omega will be omega, which is angular acceleration, angular velocity, will be measured in radians per minute, not per second, because divided by 24. Yeah, 24 hours. Or will it be per hour? Just a moment. Oh, even per hour, right? Per hour then. Yeah, sorry, not even per minute, it's per hour. Per hour. So omega, its angular velocity will be measured in radians per hour, and linear acceleration A will be measured in meters per hour squared, because usually we use meters per second squared, but this time meters per hour squared. Okay, so please make sure you use correct units. So it's per hour. If I wanted per second, I should have divided by 60 and then again by 60. Okay, if I wrote this, divide by 60 and divide by 60, that would be in seconds. If only once divided by 60, then it would be in minutes, yeah? But in this case, it will be in hours, okay? So you will find angular velocity. You will find linear velocity by multiplying angular velocity by the radius. And you will find angular acceleration by multiplying angular velocity squared by the radius of rotation. Yeah, it would be so much easier if I could write it. Can I write it here? No, I cannot. You know, I haven't learned how to use whiteboard in Zoom. Do you have any questions about projectile, angular velocity, linear acceleration, or anything else? Okay, let's try another question. Once again, I would like you to find the angular speed or angular velocity, doesn't matter, and total acceleration for the rotation motion of material point around the object with radius of t meters and constantly this linear speed of s meters per second. Yeah. So as I told you before, omega, which is angular velocity, is going to be equal to linear velocity divided by the radius of rotation. Okay, we haven't proved this in our class. We really need to draw a lot. We need to draw a lot, and it's kind of hard for me to do it in Zoom. I hope we will meet one day in the classroom so that I can draw everything very easily and I can show that to you. But for now, we need to know that angular velocity is equal to linear velocity divided by the radius of rotation, right? Your linear velocity is your student number in meters per second, and the radius of rotation is t meters per second. So that's how we find angular velocity, linear velocity divided by the radius, okay? And linear acceleration, just like before, is radius times angular velocity squared. So we need to know that as well. So linear acceleration, because of rotation, with the same speed as, the speed is the same, but because there is rotation, there is change in direction of the velocity, there is acceleration A. So if you move with constant speed, but you change your direction, it means you change your velocity. It means that you must have acceleration. And that's how we calculate our acceleration. Radius times the angular velocity squared. And we find angular velocity by dividing our linear speed by the radius. Okay? Any questions at this time?
Sir, I want to ask
Yeah.
question.
Yeah.
In general, what are angular velocity and linear acceleration used for in the field of physics, or it's still used for
Okay.
bullet or playing footballs?
Yeah. For football, yes, it can be. For bullet, not so much. We talk about the point which is rotating. Your soccer ball can rotate, can turn, whereas bullet follows the trajectory. For bullet, no, it's for the objects which are rotating. For example, you and I now on Earth, and Earth rotates, so it influences us. So we experience acceleration. We experience linear acceleration A because of rotation of the Earth. So this acceleration tries to pull us away from Earth. It's a small acceleration. It's very, very small. So it doesn't really pull us much, but it is non-zero. And maybe if we have time, we can calculate this acceleration. I think I asked you to do that maybe a little bit later. Yeah. So maybe last week we did this. We calculated acceleration due to rotation of the Earth. And it is significant because if you need to measure weight of something, so basically you minus the force, which is centrifugal force, which is your linear acceleration due to rotation of the Earth times your mass. So you become less heavy on Earth because of the rotation of the Earth. And not only you, other objects like trucks, trains, and ships, and everything. And it's very important to know the weight of those objects, because people must calculate the strengths of trains, of cars, of airplanes, of ships. We need to take this into account when we do the calculations of buildings, for example. How can the building react, just to be sure that the building is stable enough, the building is strong enough. We need to take this into account. Yeah. And angular velocity, well, it is mostly used to calculate acceleration. And if your angular velocity changes, then you have angular acceleration. So you rotate faster and faster and faster, or slower and slower and slower. But even if you rotate with the same speed, if you rotate with the same angular speed or angular velocity omega, you still experience acceleration A. You still experience acceleration. Yeah, that's the thing. You may say, oh, why am I accelerating if my speed is the same? Yes, your speed is the same, but your velocity changes because you change the direction of your motion. You go around the circle. So at first you move this way, then you move this way, etc. So you move in a circle. You move in a circle. And because you move in a circle, your velocity changes its direction. And it means, according to the second law of Newton, that you are experiencing acceleration. Does it help a little bit?
I understand, sir. Thank you for that answer.
I hope so. So basically, what we do here is usually used to calculate the strength of buildings, of cars, of airplanes, of trains, because it gives the force which those objects experience. Yeah. And when we do the calculations of strength of the trains, the cars, we might need to take those forces into account. They are quite significant, maybe like 1% or 2%, but it is significant. It is pretty significant. Yeah, okay. So if you don't mind, let's move to the next slide, number 19. I would like you to calculate the potential energy. So potential energy is, in our case, mgh. Here m is your mass, g is the gravity acceleration, which is approximately 10 meters per second squared on Earth, and h is the height above the ground, for example. So now I am in the hotel on the 15th floor. So that means about 45 meters above the ground. Yeah, so I have this potential energy. Yeah, if I drop something from my window, it has significant potential energy. It can hit something. For example, if there is a car downstairs, and if I drop something, let's say, I don't know, maybe a book or something like that, right? The book will hit the car and maybe damage the car. Maybe it will be damaged because the book has potential energy. It's above the ground, and when it falls, potential energy is converted to kinetic energy, and then my book starts moving faster and faster and faster and faster, and eventually hits the car or whatever is downstairs and cause some damage. So I ask you to calculate your potential energy. So your height is equal to your T number, for example, 15 meters, maybe in this case, 12 meters. And M is your mass, your student number, mod 35, for example, let's say 27 kilograms. Let's say it's something like pretty massive. Yeah. And your height is, just like I said, in my case, 12 meters, right? Because in my case, T is 12. For the student number, T is 12, right? So the height is also T, or is T, yeah, correct. The height is T, and G is 10. So you go your mass, which is, for example, 27 kilograms, and then your G, which is 10 meters per second squared, and your H, which is, in this case, 12 meters, right? And that's how you calculate your potential energy. And once again, we need to know, can the car tolerate this hit? Is it too strong? Will the car be damaged if I drop a book from my window, or whatever, whatever is downstairs? Will it withstand this hit? So that's why we calculate those things like velocity, acceleration, potential energy, kinetic energy, which is the next slide. So here I ask you to calculate kinetic energy, and kinetic energy is the energy of motion. In this case, it's m times v squared over 2. Yeah, just like I said before, for the gravity force, potential energy is converted into kinetic energy. For example, when I am about to drop my book from my 15th floor, when I keep it on the 15th floor, it has potential energy and no kinetic energy. The moment I release the book, my potential energy converts gradually to kinetic energy, and ultimately, when the book hits the ground, there is no potential energy anymore. All energy has been converted into kinetic energy, into the velocity of the book which is falling, okay? And that's what I'm asking you to do. I'm asking you to calculate the kinetic energy for your mass, in this case, whatever, 27 kilograms, and for the velocity of 12 meters per second in my case, right? So this is expression for kinetic energy. Any questions? So the next section is about definitions. We defined physical quantities, what we mean by what. So we know that the distance is the total movement of object without regard to direction. In other words, if I move, for example, in circle, my distance is my circle, let's say 20 meters, doesn't matter, whatever the distance is, right? But my displacement, which is the next definition, right, is going to be 0. For example, I calculate from the same point, and again, when I get back to the same point. So I made the total circle and I got to the same point. My distance is, let's say, 20 meters, but my displacement is 0 because I left the same point and I got back to the same point. In other words, displacement is the distance moved in a particular direction. Yeah. So, for example, distance is going to be, let's say, for example, this kind of path, complex, but the displacement is going to be the vector connecting initial point and final point. of my motion. Yeah. So displacement is a vector, whereas distance is a scalar value. Distance is just a number, and displacement is number and direction to it. Yeah. Just like speed is just the number, and velocity is the number and direction. Velocity is v, it's a vector. Speed is s, it's a scalar value. S scalar means just the number, just one value. For the direction, you need one number for the value and either one angle of release for projectile, for example, or in three-dimensional space, you need two angles of release and then third direction. So for 3 dimensions, you need three things for vector, either 3 coordinates or the magnitude of the vector in 2 directions. Yeah. Okay. We know that mass is the measure of resistance to change in motion. This is inertial mass. Yeah, from the second law of Newton or from the first law of Newton. Yeah. But there is also gravitational mass, which is the measure of strength of gravitational force. Here in classical mechanics, we don't really consider much of a difference between center of mass and center of gravity, between Newtonian mass, inertial mass, and gravitational mass. We consider them to be the same or almost the same, but the general theory of relativity proves that they are actually the same. So maybe if we will be dealing with general theory of relativity of Einstein, maybe we will try to prove that inertial mass is the same as gravitational mass. Okay. Any questions? Okay, the next slide. We continue with definitions. We define speed as a scalar quantity that equals to how far the object has moved divided by time taken. In other words, you divide your distance by time, and this is your speed. And this is going to be just the number, the scalar quantity, just one number, right? But velocity is the quantity that designates how fast and in what direction a point is moving, right? In this case, velocity is going to be equal to displacement divided by time, right? Okay. The next, momentum is the product of mass of particle and its velocity. That's linear momentum, mv. So I write m times v, mv, linear momentum, yeah? Angular velocity is rotation rate showing how fast object rotates. This is omega, remember omega. Omega, which is equal to linear velocity divided by radius of rotation. Okay. Okay, the next group of definitions. Angular acceleration is the time rate of change of angular velocity. That's what we've been discussing a little bit. Remember, I told you that maybe you will rotate faster and faster and faster, or slower and slower and slower. In this case, you will have angular acceleration. Okay. And the important thing for solids is moment of inertia. It's resistance to angular acceleration. So just like mass is resistance to linear acceleration, moment of inertia is resistance to angular acceleration. And as you can see, the simplest moment of inertia is equal to mass times the radius of rotation. If you have stick, and then at the end of stick you have a mass, let's say 1 kilogram, and you rotate the stick, the moment of inertia is going to be the mass of this thing times the square of the length of the stick. Okay. I really wish I could draw that. I hope I can draw. Or how about I use this draw? No. Maybe later. I don't want to make things more messy. Okay. Next, angular momentum is moment of inertia times angular velocity. Just like linear momentum is mass times linear velocity. Same thing here. The mass for rotation is moment of inertia, and velocity for rotation is angular velocity. So moment of inertia times angular velocity for rotation. Okay. And the acceleration is the rate of change of the velocity of an object with respect to time. Yeah, we are talking here about linear acceleration, the one which we have been discussing from the very beginning, and the one which is constant for projectile. For projectile, linear acceleration is the gravity acceleration, and it is approximately 10 meters per second squared. Any questions about definitions of the physical quantities, or about projectile or kinetic energy or potential energy or anything else? I'm still thinking about this question, whether you can stop the train or not, and about this question, how classical physics is related to information technology. I'm still thinking, and maybe by the end of today's meeting, I will try to answer those questions. So any questions? Okay, let's continue then. Now, time establishes the sequence of events. Here in classical mechanics, we don't really analyze time very much. But when it comes to the special theory of relativity or general theory of relativity, then we really need to explore the definition of time. Maybe time is an extra dimension, or maybe time is something special, something specific. We really need to know what time is and how it works in physics. But in classical physics, in classical mechanics, we say that time determines what happened first and what happened next. For example, last year we had the Soccer World Cup, right? It was in the past. And this year we have, for example, Australian Open, and we have Women's Soccer World Cup this year, 2023. So 2023 is later than 2022, for example. And in 2024, we will have Olympics. So 2024 is after 2023. So that's basically how we use time in classical physics. We don't really analyze time notion deeply enough. Okay. I mean, compared to special theory of relativity and general theory of relativity. And maybe today we will be dealing a little bit with special theory of relativity. Okay. Okay, the next physical quantity to define is torque, or moment of force. It's the measure of how you can rotate a solid. So the measure of force that can cause an object to rotate about its axis. So if I rotate something, let's say my laptop, right? I apply the force, and there is a distance from the pivot around which the rotation happens and the force. And this distance times the force will be equal to torque, or moment of force. Okay. We will deal with force a little bit later in more details. But here I would like you to explain in your own words the definition of those physical quantities, like distance, displacement, time, speed, velocity, linear acceleration, linear momentum, angular velocity, angular acceleration, angular momentum, moment of inertia, force, and torque. Okay, and we will discuss force next on slide 25. Yeah. So force changes the motion of the body. Force causes acceleration, according to the second law of Newton, right? So we can write that a force is equal to mass times acceleration, according to the second law of Newton. Yeah. So forces changes motion of the body. Force causes acceleration, so the velocity of the body will be changed. Okay. So in physics, by nature, forces can be gravitational, electromagnetic, nuclear weak, and nuclear strong. There are 4 types of forces. And basically, if you analyze forces deeply enough, you will see that all forces are volume forces. But in classical mechanics, we can also consider some surface forces, such as, for example, friction. Friction is a surface force in classical mechanics. Yeah. By application, the force is a surface force because friction is in between the bodies. For example, I'm sitting on the chair, so I'm not sliding down the chair because there is a friction keeping me from sliding down the chair. Okay. But volume force acts on all particles of given body. For example, gravity acts on all particles of my body. Like electrical force, like electrostatic force acts on all particles of the body. Okay. So you need to distinguish between surface forces such as friction and volume forces such as gravity. Okay. Okay. Any questions at this time? Okay. I would like us to move to static equilibrium. And I would like us to know, if we don't know yet, that static equilibrium of material point means that all forces applied to this material point cancel out. They're zero. For example, I'm sitting on the chair. My weight is, for example, 700 newtons, but the chair pushes me back with the same force of 700 newtons. So I and the chair are in static equilibrium. I'm not moving and my chair is not moving. Okay. But static equilibrium for mechanical system is a little bit different because mechanical system has size. And for mechanical system, not only all forces must be zero, but also all torques must be zero, so that the mechanical system is in static equilibrium. Okay. Yeah, and I ask you to solve the pulley problem for static equilibrium. Remember, the pulley problem, let me show you maybe in the last week's presentation. Let me see. Oh, is it not here? Just a moment. It should be here somewhere. Oh, here we go. So here, pull. Can you see? Static equilibrium will be when this mass, blue mass, is going to be the same as red mass. In this case, blue mass is 8 kilograms and red mass is 5 kilograms, so there will be no equilibrium. The blue mass will overcome, the blue weight, the weight of the blue mass will overcome the red mass and it will move down here. The blue will move down and the red will move up, okay? But if the masses are the same, then this pulley system will be in static equilibrium. Do you understand? Hello? Hello? Can you hear me?
Yes, sir. We can hear you.
Do you understand that the masses must be the same for static equilibrium? If masses are the same, it will be in static equilibrium because the weights will cancel each other out and the pulley system will be in static equilibrium. Okay. Maybe we can understand that a little bit later. I'm asking you to show that static equilibrium happens when both masses are the same, okay? And I would like you to know more about the moment of inertia, which is the resistance already. Okay, so I think we have finished kind of simplistic classical mechanics, meaning projectile, potential energy, kinetic energy, static equilibrium, discussing of definitions of different physical quantities. And now I would like us to move to black hole, which may be a little bit strange because many people think of black hole as something which is far beyond classical mechanics. But surprisingly enough, black hole can be analyzed using classical mechanics. Okay, so let's look at slide number 28. Yeah, a black hole is a cosmic body with extremely intense gravity, from which even light cannot escape. Okay, but we will analyze the black hole using the hole. 4K gram desk, let's say 10 kilograms desk. It says that my internet connection is unstable. Can you hear me?
Yes, sir.
Okay. So here is the code which solves the problem. Let me show you how it works. So here is the equation for the escape velocity. Remember, for the Earth, the escape velocity is 11 kilometers per second. So if you want to fly to the moon, for example, you must move with the velocity of approximately 11 kilometers per second, right? But speed of light is 300,000 kilometers per second, right? So it's much faster. Much faster, okay? So if we plug the speed of light c as the escape velocity, we can still calculate the radius of the black hole, which is going to be equal to 2 times the constant g, which is approximately 6 times 10 to the power of minus 11, and the mass, in this case, mass of our desk. So if we squeeze our desk to the size of the black hole's radius, which will be very small, then our desk becomes a black hole. Okay, so you can make a black hole out of any object. You can make a black hole out of your pen, out of your laptop, out of your pencil, out of everything, according to this theory. As long as you can squeeze it very hard, so it becomes very small. Yeah. So as you can see in this equation for r, this is the radius of black hole. G is the gravity constant. R is the radius of the black hole. G is the gravity acceleration. M is the mass of the object. And V is the escape velocity. And C is the speed of light. Okay. So now you can calculate, how you can make a black hole out of any object which has mass. Doesn't matter anything about the object, only its mass matters, and it matters how much you can squeeze the object. If you can squeeze it very much to very small size, you will end up having black hole, which will suck everything around it. Yeah. If something gets into the black hole, it is crushed by extreme gravity. Even the light cannot escape the black hole. Yeah. But the truth is that the black hole is actually a mystery for science and for physics. Okay. And even special theory of relativity and general theory of relativity, they cannot explain black hole well enough. Even modern physics cannot explain black hole fully. We just calculate the radius of black hole. If we can squeeze our object to the size which makes this object a black hole. Any questions about black hole, about classical physics, about anything? Okay, then another slide will be about using special theory of relativity in classical physics, okay? I ask you to assess time, mass, and size when you move with the speeds close to the speed of light. For example, 0.9 of speed of light, this one. It's quite close to the speed of light. And if you can calculate the square root, it will be significant, right? So if supposedly your velocity v, is equal to the speed of light, then 1 minus c squared over c squared will be 0. In other words, I become infinitely massive, my mass becomes infinity, my size becomes 0, I become infinitely small, and my time stops, okay, according to this. But we cannot move according to classical physics laws, we cannot move with the speed of light. We move slower than the speed of light. For example, if you move with 0.9 of speed of light, it will mean that you will become twice as massive, twice as small, and your time will be 2 times slower than the time of someone who is not moving. Yeah, you slow down your time if you move fast. Okay. So basically, if you want to use classical mechanics for very high speeds, you must multiply your mass, your size, and your time by this square root, which is expressed through your velocity and speed of light. Okay. So here, this is this simple code which calculates how many times your time slows down, how many times you become more massive, and how many times you become smaller, depending on your velocity v. If you move very, very, very fast, then you become smaller, you become more massive, and your time slows down. Any questions about special relativity in classical physics, about black hole in classical physics, and about anything like projectile, kinetic energy, potential energy, or anything else?
Sir, I want to ask,
Yes.
is the speed of light constant in our reference frames?
Wow, indeed, that's a great question. Look, usually we consider speed of light as like maximum speed, and you know, maybe you get it from the internet, but you cannot really ask that kind of question about any speed, including the speed of light. We cannot say that speed is constant or not constant, because speed is measured in meters per second. If you ask whether speed of light is constant, then basically you ask whether meter is constant and second is constant. Yeah. So
I
it may be
understand.
difficult to understand, but my PhD thesis was about constants, physical constants, and I proved in my PhD thesis that you cannot say whether speed of light is constant or not, because this question makes no sense. You can ask me, is your speed divided by speed of light constant? That's a legitimate question. Because if you divide one speed by the other speed, you have dimensionless physical quantity. You have no dimensions. Yeah.
Okay, sir.
But
Thank you for the
many
answer.
people, yeah, but the truth is that many people still discuss this question, and many people write even scientific papers on whether speed of light is constant or not. But if we analyze this deeply enough, we just cannot say whether speed of light is constant or not, because this question does not make much sense. You can say that, for example, is angle, for example, is constant or not, because angle is measured in radians, and radians are dimensionless. Yes, the angle is constant. Yes, the ratio of speeds is constant, but we cannot talk about, let's say, is this distance constant? For example, is the distance from Jakarta to Surabaya constant? We cannot talk about that because distance is measured in meters. And if you talk about constant distance or constant speed, then you must talk about, is the meter constant? Of course, meter cannot be analyzed in this way, because meter is just a quantity. It's a physical quantity. It should be measured. The physical quantity you want to talk about in terms of its change must be dimensionless. It must be dimensionless. It must be some kind of ratio. Okay, this is very, very complex question, which goes far beyond our course. What we can analyze to be constant, and what cannot be constant, and what has no sense if we discuss whether it is constant or not. So we cannot really discuss whether any dimension-full physical quantities are constant or not. We can only discuss whether dimensionless physical quantities are constant or not. Okay, and many people with PhDs think that they can discuss change of speed of light, but the truth is that you just cannot discuss this question. It makes no sense. So I'm not surprised if you took it from the internet and those people didn't analyze that issue very deeply. Yeah, I hope it answers your question a little bit.
Okay,
But
sir.
I
Thank you.
understand that, yeah, my answer is so complex, because the question is very, very complex. Yeah. Okay. Surprisingly enough, there is chaos in classical mechanics. So remember, we discussed pendulum, but if you attach one pendulum to another pendulum, you will have double pendulum. Okay, and double pendulum, surprisingly enough, is chaotic. Remember, I wrote equations of, for example, equations of projectile. In projectile, everything is predictable. At any time, you will know where your projectile is located. You will know speed of projectile. You know everything about your projectile at any time. But surprisingly enough, for double pendulum, we cannot predict what is going to happen. It looks like it is just a simple mechanical system, but double pendulum is chaotic. It's chaos. We need to use statistics to analyze this. Remember, I showed you a special relativity in classical physics. I show you black holes in classical physics, and now I show you chaos in classical physics. So surprisingly enough, there is chaos in classical physics. For example, double pendulum. And if you go to this Wikipedia website, if you scroll down, you can see that, or maybe I can show it to you, by the way, because I'm sharing the screen. Let me try to show it to you. Okay. Can you see that? Double pendulum. Can you see one and the other one? And I hope you will see the chaos. There we go. Can you see? Can you see how chaotic the motion is? Can you see that?
No, sir.
Can you see the chaotic pattern of double pendulum?
In the screen, your is PPT, sir, not Wikipedia.
Can you see my screen?
The screen is PPT, sir. PowerPoint.
Oh, still. Oh, I'm sorry. I'm sorry, PPT. Let me show you. Sorry. Sorry. Thank you. Where is it? Oh, there we go. Sorry. Thank you. Can you see this? Can you see Wikipedia? Can you see? Hello? Yeah. Can you
Yes,
see
sir. I
that?
can see. Yeah. Yes, sir.
Okay. Okay.
Clear.
Thank you. I didn't know. I thought that whatever I see on my screen, you also see. Thank you. Sorry for that. Yeah. As you can see, it is so chaotic. You cannot predict the motion of double pendulum. And it may be very surprising because it's just double pendulum, just a simple mechanical system. Remember, we wrote the equation for single pendulum, and the equation is just sine. Y is equal to sine omega t, and that's it. Excuse me, let me check what that is. Oh, you have sent me some messages. Oh yeah, thank you. Okay, so okay, double pendulum. So let us go back to the slides if you don't mind. Let's share screen. Okay, share. Okay, so any questions about anything in classical mechanics before we move to elasticity? Okay, the next slide, number 34, elasticity. There we go. Elasticity is the ability of the body to regain its original shape. For example, I squeeze my eraser, and when I remove the force, the eraser gets back to the previous shape. Yeah, that's called elasticity. And elasticity is described by Hooke's law, very similar to the spring law. Okay, force is equal to some constant times x, where x is displacement. Yeah, and elastic energy, just like kinetic energy, elastic potential energy is going to be half of kx squared, right? We know that the work is going to be force times the distance. Force is kx and the distance is half x when you calculate the force, when you calculate the integral. So half x times x is half x squared times k. This is going to be potential energy of deformed spring. And there is conservation of energy for elastic force. As you can see, the force is actually derivative of the potential energy of the force, and it is a sign that the elastic force is potential force, and there is conservation of energy of elasticity. So the energy of elastic deformation is converted to kinetic energy of motion of the spring or whatever the object you squeezed. Okay, so maybe I can show you elasticity. Just a moment. I stop sharing this, and I show you elasticity. I will try to show you elasticity in just a second. I want to show you elasticity. elasticity, and let me show you images. There we go. Elasticity. Mhm. Okay, elasticity. I cannot find it very quickly. Okay, maybe later. Okay, I will try to share the screen again. Share the screen. There we go. Okay, elasticity, just like I said before, is the ability of a body to regain its original shape. Just like spring, after someone applied force to spring will be squeezed, and then when the force removed, the spring will go back to its original shape. Okay? But for the plasticity case, the deformation is irreversible. Plasticity means that the body does not regain the original shape. For example, I take, let's say, an apple, and I squeeze an apple, so I crash it. So the apple will not regain the shape when I remove my force. So that is example of plasticity. Or if you take clay, probably the best example would be clay. You can squeeze the clay, so the clay will change the shape. And when you remove the force, the clay will stay the same. It will not regain its original shape, okay? So let me show you the graph showing the elasticity. So the red thing is elastic part. So we plot strain, or just displacement, against stress or force, doesn't really matter, right? So this red section is elastic. So if I apply the force here, or stress, doesn't really matter, and I removed it, it will go back to the original shape. And up to H point, it will go to original shape. But after H, as you can see, it becomes nonlinear. The elastic phase is linear, it's a straight line, right? But after elastic phase, it becomes nonlinear. And if I apply more force and more force and more force until point P, if I release the force, as you can see, it will not regain the shape. There will be some change into the shape of the body, okay? And if I put more and more and more and more load, eventually it will collapse, it will fail. The fracture will occur, okay? The fracture will occur. So for example, if I squeeze my pencil, eventually my pencil will collapse. So there will be fracture, the pencil will collapse, and I will have broken pencil, okay? So we also must know, I mentioned that here, that the physical nature of elasticity, plasticity, and fracture is electromagnetic. So if we analyze classical mechanics very deeply, then eventually we will get to electromagnetic forces, which are volume forces, which are the topic of another chapter of physics, electromagnetism. Usually we study mechanics first, then thermodynamics, then fluid dynamics, and usually after that we study electromagnetism, right? But if you analyze elasticity, plasticity, and fracture deeply enough, you will find that the physical foundation of these processes is electromagnetism. In other words, attraction and repulsion between charges, okay? Okay, so I ask you about the pulley problem once again. Oh, I have realized that you didn't see the pulleys because I didn't switch my screen. Oh, I'm really sorry. I didn't know. So the question asks you, what must the masses of the simple pulley problem be? Must be the masses in a simple pulley problem, to break the rope, if the breaking point of the rope is 10 newtons, Let me show you the pulley problem. Let me stop sharing this and let me share another one. There we go, this one, right? Share. Can you see the pulley? Just a moment. Can you see that?
Yes, sir.
Yes,
Can you
sir.
see that? Yeah, I'm sorry. I thought you saw this, but it seems that you didn't see. So in order for the pulleys to be in static equilibrium, the masses must be the same. The blue mass must be the same as red mass, okay? And if the breaking tension is T newtons per second, T newtons, not per second, T newtons, it means that the weight of both pulleys, weight of each of the pulleys must be T divided by M, right? So basically, the tension in the cord will be equal to mg. I'm sorry, T is equal to mg, where M is one of the masses. The masses must be the same. For example, if your T is 10 newtons and then the cord fails, right? Then it means that your mg must be 10 newtons. And if mg is 10 newtons, it means that the mass must be approximately 1 kilogram to break the cord, to break the rope in this pulley problem, okay? If your T is 10 Newton, then it means that to break the cord, you need mass of 1 kilogram. If your T is 20 Newton, then it means that you need 2 kilograms. If your T is 5 newtons, then you need half kilogram mass to break the cord, okay? So I stop sharing this, if that's okay. And let me see, share. Let me go back to fraction. Okay, I hope you can answer this question. Any questions about anything? Okay, the next we move to fluid. Let me see, fluid. Can you see fluid? Pressure is equal to force divided by area. Pressure is equal to force divided by area. Can you see that? Hello, fluid. Can you see fluid?
Yeah,
The
yeah.
word fluid. Okay.
Yes, sir.
So the pressure in a fluid is equal to rho gh. Here, h is just height, just like before. Rho is the density of the fluid. G is the gravity acceleration, just like before. And in order to prove this formula for pressure, P is equal to rho gh. And in order to prove this equation, we need to use area, which is A, and we need to use volume, which is V. And here is the proof. Pressure is equal to force over area, and also pressure is equal to force, which is mg, divided by area, and m mass is equal to rho density times V. In this case, V is the volume. And volume is equal to area times the height. You plug all the letters in, you cancel out the area, and indeed you have that pressure is equal to rho gh. So pressure in fluid at depth h is equal to rho gh, where rho is the density of the fluid, g is the gravity acceleration, and h is the depth of the fluid. For example, at the surface of the fluid, h is 0 and pressure is 0. But let's say 1 meter deep with rho of 1, kilogram per cubic meter, you will have pressure being 1 Pascal. So 1 Newton over meter squared, right? Because the density is 1, H is 1, I'm sorry, it will be 10 pascals because G is 10, right? So if height is 1, if rho is 1, then pressure will be 10 pascals because G is equal to 10 meters per second squared, right? Okay. Okay, let's continue and see what, so yeah, prove the pressure of the fluid is rho GH. We just proved that. I hope you can prove it if necessary. Any questions about fluid, about fracture, plasticity, elasticity, projectile, kinetic energy, potential energy, rotational motion, about anything? Okay, then next slide. Basically, I ask you to calculate the fluid pressure, rho GH. Yeah. So I give you rho being A is your student number mod 25, your H is T, and then G is 10, yeah? You just calculate pressure as rho GH. Just a simple equation, yeah? Later on, hopefully, we will learn that pressure is directly proportional to the average velocities of the particles, but that will be later on when we study thermodynamics, hopefully. Okay. Okay, and next slide shows Bernoulli principle. Remember when I blew below the paper during our first meeting and the paper went down? I hope you remember this Bernoulli experiment using Bernoulli's principle. Do you remember when I blew below the paper? Hello? Do you remember during our first meeting, I blew below the paper and the paper went down? Do you remember
Yes,
that?
I remember, sir.
Okay, so that's Bernoulli's experiment using Bernoulli's principle, which is basically conservation of energy. Can you see rho GH here is basically pressure. Pressure plus kinetic energy half rho v squared is going to be a constant value. It's a constant value. Conservation of energy. So the greater the velocity, the lower the pressure, and vice versa. The greater the pressure, the lower the velocity. And remember, when I blew below the paper, velocity increased below the paper, which means pressure decreased. So it means that the pressure from above the paper pushed the paper down. Yeah. Okay. If there are no questions so far, I would like us to talk about Magnus effect. If you like playing soccer or if you like watching soccer, you can see that sometimes when they kick the ball goes not in the straight line, but in curved line. For example, you can score from the corner point. Yeah, so you curve the ball. Yeah, and this is due to Magnus effect, and it is due to the Bernoulli's principle again. Yeah. When the ball rotates and moves on the one side, the pressure becomes bigger because of the fluxes of air cancel each other out, and velocity is smaller. The pressure is bigger, and on the other side, velocities add up, so velocities become bigger. The pressure becomes smaller. So therefore, bigger pressure pushes against smaller pressure, and the ball moves in the curved path. So I would like you to briefly explain Magnus effect in fluid mechanics. Any questions? So we almost finished with the slides. And if you have no questions, I would like you to know this equation of thermodynamics of heat transfer. This is heat transfer equation. Yeah. Yeah. So just like in classical mechanics, potential energy wants to become kinetic energy to make sure that the potential energy is minimum, right? Here in the thermodynamics, heat is transferred from hotter body to cooler body, okay? And this heat transfer equation that you can see on slide 43 shows you how the heat will transfer in one-dimensional road. So, for example, there is x kind of dimension on the x dimension, space dimension on the x, so it's one-dimensional road, and then you hit one of the ends of the road, and then the heat is spread along the road. Yeah. So this is the differential equation, dH over dt, which is time, h is heat, is equal to constant d, the transfer constant, times second derivative of heat with respect to x. Yeah. And the boundary condition at the infinity is 0. So very, very, very far in the infinity, it's very, very cold. The temperature is 0. Yeah. At any time. And also with time, as you can see from the solution, with time, the temperature goes down. Yeah, the temperature goes down with time. Yeah. Here, d capital is transferring constant, heat transferring constant, and pi is an irrational number, which is approximately 3.14. Yeah. You know, this equation is not only the equation of thermodynamics, but also the equation of diffusion. So that's how you mix, for example, sugar in your tea. This is the law how your sugar is mixed, is melted in the tea. Yeah. And moreover, this equation also tells you how information is spread in a society. And you, as information technology people, may be interested in this process. Okay? And I will tell you even more that a very similar equation is used in business and economics, very similar to this equation. And people got Nobel Prize for this equation in economics in 1997. So this is a very famous equation, and I hope you understand this equation. And maybe you can prove it. I mean, not the actual equation. You can prove that the solution is correct by just plugging the solution into the equation. But if you don't want to do that, it's okay. It's pretty complex proof. It will take maybe half an hour to prove. Yeah. Can you hear me?
Yes, sir.
Hello. Do you have any questions or comments? I think we have finished our slides for today. Maybe if you have questions about today's slides, or maybe last week's slides, or the slides of the previous, of the first or second or third meeting, maybe you can let me know. Or if you have any questions, any question whatsoever, please don't hesitate to ask. Okay, any questions? Okay, I think I need to go to cloud. While you think, I will try to go to, oh yeah, it's here, okay. So I will try to, oh, session number 3. Oh, mm, okay. So, do you have any questions or comments about anything from today or from last week or from 2 weeks ago? Well, if you don't have any questions, then maybe we can finish for today. What do you think? Or maybe we can discuss maybe fellowships, scholarships, maybe American citizenship. Maybe I can help you with that, or any other things which are connected to scholarships, fellowships, maybe English language, maybe American citizenship, or something like that. What do you think? Should we finish for today, or should we continue? Hello? Yeah.
Sir, I'm a bit curious about,
Yeah.
um, but my question is out of topic of the day. Is it okay?
I cannot hear you well. Could you please speak slower and maybe more loud?
I have a question, but my question is out of topic of today. Is it okay?
Yeah, yeah. Ask any question.
So I'm a bit curious about why do you choose Indonesia for work, or why do you choose Indonesia to teach Indonesian people?
Why Indonesia? You know, I am married to Indonesian woman, and I am very lucky. I'm very happy to be in Indonesia, and I want to help Indonesia. Okay, let me stop sharing for a while. Um, does that answer your question?
Can you speak language Indonesian, sir? For a bit?
Not very much. I can speak like terima kasih, like terima kasih Bu, terima kasih Pak. That's about it. I'm
Gokil.
talking in either Russian language or Ukrainian language or English language. I don't really talk in Indonesian language very much. And you know, it helps other people to practice English language with me. That's a good thing about me speaking English, because all Indonesians know Indonesian language, but when it comes to English, people usually need to practice their English with someone who doesn't speak Indonesian language.
It's cool, sir.
Yeah.
It's cool.
Can you say it again?
It's like, it's cool.
Oh, cool. Yeah. Thank you.
Yeah.
Thank you. Thank you. Yeah.
And
You
I
know,
hope
I
to
think
learn
some,
many languages from you, sir.
yeah, for how long? Yeah, I've been to Indonesia for 12 years. I've been to Indonesia since 2011, for 12 years approximately. Yeah.
And pardon, sir?
Yeah, I have been to Indonesia for 12 years. Let me write it down.
Wow.
Does it answer your question? I have been to Indonesia for 12. I write it in the chat. I have been to Indonesia for 12 years. In English is your mother language, sir? No, no. My mother languages are Russian language and Ukrainian language. Ukrainian, sorry. Yeah. My mother languages are Russian language and Ukrainian language.
Wow, sir.
Yeah. I'm from Ukraine. I'm originally from Ukraine. Yeah, maybe you have heard about Ukraine. I'm from Ukraine. Have you heard about Ukraine in the news?
Yeah, yeah. Recent versus Ukraine.
Yeah, a lot. So that's why I think we really need to be careful so that you will not have. Okay, I thought English is your mother language because. Oh, thank you so much. I wish my English was much better, but I really appreciate your opinion. I really like your opinion that you think that my English is good enough. I'm studying English. I'm learning English. I'm trying to improve English. I also teach English to some students. I teach speaking English. Sometimes I teach a little bit of grammar. Sometimes I prepare students to go to foreign universities in Europe, in the United States, in Australia. So that's what I'm doing on Thursdays and Fridays, usually. Yeah. Any other questions? That's so nice.
Sorry, sir.
Yeah.
Can you share the PowerPoint to us in our group chat, sir?
I think I shared. Can you see? I gave you the link. Let me see. I gave you the link to the PowerPoint. Can you see? It was, I asked you, will you join the Zoom meeting? Or do you want me to share the file? Let me try to share the file if you want. Document, poll, camera, news. Okay, let me try. Okay. Oh, just a moment. Oh yeah. Okay. Can you get it from the link I gave you? I can share the file if you want, but I think you have the link. Yeah, it's lecture number 3. It's called 3PPT3 phase 23rd September.pptx. Yeah. If you cannot get it from the website, from this link, then I will share the file in the group chat. Yeah. Okay. Any other questions?
That's enough, sir.
Yeah. Yeah.
That's enough.
Okay. So should we finish our meeting for today? Yeah.
I think yes, sir.
Okay. Thank you so much. Please enjoy your evening. Thank you so much for your time, for your patience, and for your effort.
Thank you, sir.
Thank you,
Спасибо.
sir. I appreciate you. Thank you so much.
Спасибо.
Yes,
Спасибо.
спасибо.
Yeah, that's in Russian. Wow. You learn
Yeah.
Russian language. Thank you so much. Terima kasih banyak. Terima kasih banyak. Please have a great evening. Thank you. Bye-bye.
Thank you, sir.
Okay, sir.
Uh,
Thank you. Good night.
Thank
Thank you so much,
you.
sir.
Bye-bye. Thank you.